As I mentioned, there are a ton more tricks that are used for text search that we don't tend to look at in relational databases that have a more general purpose workload. One of them that we didn't discuss is to do faster postings lists intersection than a simple merge join would do. And in essence, you can think of this as an in-memory multi-way merge join algorithm. I have many of these postings lists. They're all going to have their prefixes at least in memory, and I want to do something very efficient in memory to merge them. And these will do techniques like doing binary search within the lists to find initial pairs and other schemes you can look up in the literature on intersection algorithms. Another thing that comes up quite a lot is ranking the output. This is critical, obviously, for building a good search engine, and we'll talk about this more in the next half of the lecture, at least give the basics of that idea. A third issue that comes up is document clustering to diversify the outputs, for example, of a search. So suppose you do a search on a term like jaguar, which could return documents about large cats, it could return documents about American football, and it could return documents about British cars. And you'd like to get a smattering of each in your top 10 results so you get a sense of the diversity of answers to this query. Alternatively, in some interfaces, you might want to get those three classes of answers segmented out into different document sets. And so this idea of document clustering is something that we won't have time to discuss today, but it's of interest to folks in information retrieval for obvious reasons. Another sort of internals issue that comes up a lot in building information retrieval engines is the idea of using compression for better I/O performance. For example, compressing postings lists to make them smaller. And this plays into the postings list intersection algorithms described above. We might want to try to make the postings lists fit in RAM or even in processor cache while keeping an efficient intersection algorithm working over them. Other issues that come up more at the language level are how to deal with synonyms, misspellings, abbreviations. We'll see a little bit on misspellings in the later part of this lecture. And then more systemically, if you're building a web search engine, how do you write a crawler? How do you write an index loader? These are issues that come up when you're in production at scale, and they're very important and non-trivial. One of the trickiest things that didn't exist in search engines until the web was the idea of dealing with SEO, search engine optimization, which is the polite phrase for web spam. So when the content providers have incentives to change their documents to get them top ranked, how do you build a ranking algorithm that sort of doesn't allow people to game the system too much? And that's a challenging problem. Final issue that comes up quite often in web search, which didn't come up prior to that, is user customization. Trying to figure out, based on the user's geography or based on something you know about their past queries, what would be good answers for them in particular. So to summarize, at this point, with this simple information about essentially B-trees and merge joins, you already know the basics of how to do information retrieval. Inverted files are the workhorses of all text search engines, and that's the term you'll see in the information retrieval literature. From a relational perspective, these are just B-plus trees or hash indexes on this kind of bag of words tables of data. Okay, so we're turning documents into tables, and then we're building indexes on those tables. That's what inverted files are. And then the processing we do during querying in a search engine is intersection, union, and set difference of postings lists. And those are usually implemented via the pre-sorted postings lists and merge algorithms to merge them together dynamically. This is basically a merge join of multiple postings lists. Now it can be done, and sometimes should be done, with hash or index joins. And so the fact that you know the more than one join algorithm is handy here in thinking about if you're going to implement a text search engine. When would you not want to use a postings list? When might be better to use a hash or index join? And then, let's be clear, some of what goes on in information retrieval is custom to text and web, especially linguistics and statistics issues. Statistics in recent years on the web has proven more important than linguistics, it turns out. Interestingly, it's more interesting to know about frequencies of things than to know about language models. Exploiting the graph structure of the web turns out to be very important, as we will discuss soon. And then understanding content types and user desires, these are all things that come up in text search and don't so much come up in relational databases because, of course, in a relational database, there's no question of ranking queries. We simply provide the answer to the query that the user asks in SQL. So, to summarize, here are some buzzwords that you should know from information retrieval, at least on the content we've seen so far. As I mentioned, I taught this with respect to relational foundations, but you should know the information retrieval's terminology when you go talk to folks who are experts in the space. So a corpus is a collection of documents, and by the way, the plural of corpus is corpora, so you should know that. A term is an isolated string, so a searchable unit. You can think of it as a stemmed word. An index is a mechanism. It's not what we called an index in relational database land. It's a mechanism of mapping terms to documents. And we've seen that a search index might be essentially multiple logical tables and B trees in order to achieve an index. An inverted file, sometimes called a postings file, is a file containing terms and associated postings lists, and a postings list, as we saw, is a list of pointers or postings to documents. To summarize what we've seen so far, basic information retrieval. IR and relational systems share building blocks for scalability. Internally, the search engine is just converting text into relational tuples, using equality indexes like B-trees, using data flow, basically iterators, and what we'll see in a minute, parallel data flow, to achieve scalability, and using join algorithms, particularly merge join. Information retrieval constrains the queries, the schema, and what it promises semantically on the answers. This affects the storage formats, like compression of postings lists. It affects the indexing and concurrency control in terms of update handling. And then it affects the join algorithms and the quote-unquote selectivity estimation, because the join algorithms themselves are not so sensitive to intermediate results. They're all streaming. Information retrieval has different performance goals than traditional query processing. It's most important in information retrieval to get the top ranked answers out quickly. Right? Everything we can do to get that first page of top 10 answers first, that's the performance goal we want. Getting to the final tuple, getting the full answer of the query output, isn't even a goal in many information retrieval settings. There are many challenges in information retrieval related to the specifics of the domain. Those challenges are interesting, but they don't tend to change the scalability performance infrastructure that we learned so far. And so the basics that you know from this class will stay true. They will hold true even as you learn more about the tricks involved in text search.